Okay, previous class we learned about the crack size, fracture size. So there's a diagram for you to remember. So every time there's a tensile loading, the next phase will have a growth of cavity. Once cavity grow, it will grow into a bigger crack size, and then it will fracture. Right. So in your calculation, example 2, you learn about critical stress constant equal to Y U strength and square root of your IA. Okay. Today we learn about something new, which is called cyclic stress. Right. Previously you load and then you stop. Right. But today we learn about cyclic or repetitive stress. And we start to learn about fatigue. Fatigue. So this diagram, if you look at diagram, you can diagnose where is the origin of the fracture happen. So this is a notch. This is a keyway. It's a shaft. The shaft. Okay. So when you turn, it's like a key. Sometimes the key of your door. Sometimes your key broken. Right. So you know that when you talk about fatigue, we talk about stress concentrator. Right. Is at sharp corners. Right. So here, if you look at the surface, two stress concentrator, it is on the sharp corners. Right. And then you'll see the mark here, the mark here. Okay. The mark on the diagram, especially fracture, is called clamshell. It's like a shell pattern, or beach mark. It's like a beach mark. Okay. The rest you read. So there are two. One is beach mark. One is striation. Beach mark, that you can see very clearly like a shell mark. This one at a microscopic dimension. This one microscope beach mark means you can look at your naked eyes, right? But the fatigue striations are microscopic size. One is macro. Beach mark are macro. Macro means you can see with your naked eyes. But fatigue striations are microscopic in size, subject to observation under SEM. The one that we have in lab is not under SEM, is a macro microscope. This one you need to look under a higher powered machine, right? So this is the example under SEM, which is the fatigue striation with this zoom large size, normally in the nano scale. This is fracture surface material 6061 T6 structure. Right, so you look inside there, you see what happened. Okay. So there's a difference in this picture and this picture. Right. Okay. So there are two distinct type of surface. First, smooth surface region due to rubbing, and rough surface formed by the fracture when load become too high. Right. So there are two surfaces. One is smooth, one is rough surface. Smooth surface, normally you see somewhere here. Smooth surface is due to rubbing between the open surface region as a crack propellant. So especially here, when it open, then maybe at the beginning there, the two surfaces will rub each other. They will rub each other. A rough surface is formed by fracture. So you can see, if you're given a picture, you look at this microstructure, it's like a hairline like that. And then region of slow crack propagation. If it's slow, right? If it's slow, then you see like a shell shape. But it happened very fast, snap like that, crack like that. Then you will see like what call like a rough surface lah, like a rough surface. Okay. The rest you read, As you read. The objective here is to is to show you what happens if you have a very fast fracture and slow fracture. Okay, so you have seen this machine before in your lab session. So we will use a fatigue test to do the experiment. So you rotate, you put in the sample and then you rotate, then you count how many sample it breaks. Right? So you put in the specimen and then you turn. The weight here in your experiment is on the left hand side. You screw the 200 Newton. You still remember? On the left, on the side of the machine. And then you turn on the motor and then there's a counter. Okay. And then your sample is a bit different, but we are focusing on the same thing. If you look at the lab sheet, we're focusing on the taper size over here. So for fatigue, we will use one diagram. For tensile graph, okay, this is fatigue. In previous chapter, in tensile test, tensile means you pull at both ends until it fails. Fatigue means you have a cycle of loading. You load and then unload, load and then unload, load and then unload. So tensile test, you have tensile graph. Tensile graph where stress versus strain. But for fatigue, you have SM graph, SM curve or SM graph. What I mean by S? S is a stress. Your stress, how many megapascal or pascal? Again, look carefully when you have a graph. This graph on left hand side is imperial, right hand side is uni SI. And then the N is number of cycle. Okay. So here you have aluminium and steel. So you have you can plot lah. So what does it mean? Let's say I pick this point. So number of cycle 10 power 4 is 10,000 cycle. If you move up, aluminium will fail at stress 350. This one, go up, go left, go right. All right, it's about 350, it fail already. But the same, 10,000 here. For steel, you will fail at higher stress. Same number cycle, they fail at different stress. Okay. So for your lab, right, if you want to go deeper, you have only one sample, right? The material, did the lab technician tell you what is the material? For the fatigue, no. Okay, I presume it's a carbon steel. So you go, if you can, you go and find SN graph. for material. And then you have the number of cycle, right? You have number of cycle. So number of cycle, you have sample 1, 2, 3, but with a different dimension. But it will between the range, right? So you still remember what is the number of cycle you have? How many? 1,000 something, right? You still remember how many cycle it break? You still remember? 300. 1,003 to 1,006, right? Oh, about that lah. So it will fail. So you go to material handbook or encyclopedia, you find SN graph. Then you go and find the range 1300 to 1600. There's a line there. You can find like carbon steel or something. Then you predict lah. You predict, and then you discuss about the failure stress. Okay. This is just for your report writing. You go and find the material SN graph. You just Google lah. Google material SN graph. Then if can, you find sources from encyclopedia or material standard chart. Standard chart. You search for fatigue tests. Fatigue test for carbon steel. Then you will come out lots of graph. So you pick one that in your report you assume that the material that you use is so and so, right? So then you have the failure number of cycle. So you just on the graph, you just simulate the number of the failure point there. Then you project up. You project up. Then there is a range of failure value. Here you got 2 points in megapascal. Okay. Then you discuss this one. These two. This is from estimation of material. Okay. You can even pick from the same graph. Maybe you can pick because carbon steel you have a lot of so-called species, a lot of code there. You can compare 2 or 3 material. Then more things for you to write. Okay. Okay, the rest you read. Okay, the rest you read. Yeah, the rest you read now. Slides. Okay. Then we start to look at cyclic stresses. So on the graph here, on the y-axis is your stress. You know that when your stress is positive, means it is having a tensile loading. Tensile means you're pulling at both ends out. Then if you have a negative stress, means it's the opposite direction. So it will be compressive stress. So below 0 will be negative, above 0 will be positive. And you will see that this is on the x-axis normally is the time. Cycle. Number of cycle. So stress will go up and then go down, up and down, go up and down. Okay. In mathematics, this kind of form, this kind of curve, we call it sinusoidal form. We have a maximum stress and minimum stress on the curve. Assumption will be the rotating shaft operating at a constant speed without overload. So means that the motor rotate at the same speed. The same speed. Okay. Okay, the rest you read. Okay, there's a this graph, this sinusoidal graph maximum and minimum, you see the same curve. The A magnitude here is the same. If you measure from 0 to stress max to 0 to stress minimum, the A here is the same. I mean, the amplitude is the same, right? But if you see the second graph, the whole graph was shifted up. The whole graph was shifted up. It means this one, this graph, this sample, this experiment, you are conducting a positive tensile loading. This one, you have tensile and compression in the same in one complete cycle. All right. So by looking at the graph at degree level, you should able to see what happened to the operation. Okay, what happened to the test? Okay. Okay, the rest you read, huh? So this one is called a random stress cycle. The previous one, this one is on the repeated cycle with the equal stress max and stress min. So you can see stress max, stress min. Huh? But this one is random. It's random. There's a machine you can set, but this one normally we don't use lah. However, in a realistic application, this one will happen, especially your car absorber. Your car absorber, you don't know the road condition, so you have a random stress on the. Okay. Okay, when there's a graph, there's a calculation. So when you have in this graph on the left, you see there's a positive and negative value. You have a stress max and stress minimum, and there's an amplitude there, right? So the first calculation from the graph is to find the mean stress. Mean means find the average. So you take maximum plus minimum divided by 2. Okay, and this graph you have two stressing or two loading. One is tensile, one is compression. Okay, and we are now in a fatigue cycle. Fatigue means you are continuous repeating your loading. There's a repeating loading process. Then another one is the range. The range of stress, you take the maximum point and the minimum point. The two peak, one is on the tension region, one is in a compression region. Then you have the range of the stress. So we use sub R in the textbook. Okay. So just now we show you three graphs. One is the one you see on the screen here. Another one we shift the whole graph in the tension region. Another one is the random spectrum. Okay. Now to find the amplitude, stress amplitude, I mean the you can say the peak or the height of the stress. But in material we use the word amplitude. So we just divide lah. You take the range divided by 2. How to calculate range? You take the maximum peak plus the minimum peak divided by 2. Right? Then the stress ratio. Stress ratio is between the minimum and maximum. You take the minimum point divided by maximum point. Okay. So you have 4 equations. Once from the graph, you find mean. Mean is max plus minimum divided by 2. Range is maximum minus minimum. Amplitude is take the range divided by 2. Stress ratio, you take minimum divided by maximum. Okay. Next, we look at how fatigue process happen in the ductile metal. So we have ductile and brittle material. So now we look at how ductile metals happen when it was subject to fatigue process. Right. So I'll give you all, give you all. Okay. First is the crack initiation. Right. Then second, slip board crack will grow. So you can see from the left to right, A, B, C, D, E. So when there is a fatigue, either tensile or compression, the material will start to crack. Right. So on the diagram A here, you see there's a slip source happen. Source happen. And the rate of the crack growth is happen very, very slow. For metals, there will be 10 power negative 10 meter over cycle. 10 negative 10 meter, it will be 100 pico meter per cycle. Very, very slow. Okay, then if you see diagram A to E, what happened is that the slip source initiated, then it start to slip. You see there is a transition of slip plane. So there's a two plane was slip. So you can see the first on the top here and the bottom here, right? And then see it start to develop the crack already. Start to develop the crack. So this is on a microscope dimension. This is a slip band growth. This is on a copper single crystal. See the slip plane here. This is the polymer, where you learn in your last chapter of this module. So polymer dots. This is the crack that slips. Okay. So the on the right diagram here, it's like a steel inside the concrete. Then there's a resin put inside there. Then when the fatigue happen, it will just crack like that. Okay, that's why you see there's a straight line on the microscope slides here. Okay. Then the third phase or third process is crack growth on the plane of a high tensile stress. So in this stage two of crack growth, this one you read, huh? So here, fatigue stration happen. Okay, we have two type of fatigue phenomena. One at the macroscopic, one at the microscopic. Okay, this one also you read from the slides. Then there's the ultimate ductile fracture. Okay, ultimate. So okay. Number four here, ultimate means is broke into pieces. Already can peel into two pieces already. Okay, I'll give you all. So one area that we can assess you is ask you about what are the factors that can contribute to the or affect the fatigue strength of the metals, right? There are a few. First is to stress concentration. Now, 8.2.3, it will affect how you design your products. How you design your product, how you avoid your product from fatigue failure. You judge based on all these major factors. Huh? First is stress concentration. The stress concentration. So stress concentration is the area where you have the crack start to happen. So why are the stress concentrator? It will be be careful on the stress racer area. For example, there's a keyway, sharp corners in the cross section. Right? So you can compare design A and design B. Design A will fail very fast compared to design B. That's why in your lab experiment, when you do the fatigue, sample 1, 2, 3, the radius of the fillet is different. If you look carefully, the diagram that we given to you, sample 1, 2, 3, there is a cutting radius at the head there. Then they will see there's a change of failure cycle. So those have a smoother round surface, supposed to have a higher end cycle. Okay, so this one you should able to observe from your experiment. Okay, so here again, first avoid stress concentration, or look at the stress concentration. Avoid stress eraser in your design. That's why nowadays, most of the consumer products, we like to have a round surface, or round fillet corner. Okay. One is it looks better. Another one on mechanical properties, we know that when we remove those sharp corners, we actually improve the material properties, especially when it comes to fatigue scenario, right? Like those engine parts. Engine parts, we would like to have them in smooth corners because they keep moving in lots of cycle in the operation. Number 2, surface roughness. First is you look at the stress eraser or stress concentration. Second one, you look at surface roughness. The smoother the surface finish of the metal sample, higher the fatigue strength, meaning it failed at a higher end cycle. Right? Now, why smooth surface able to withstand stress? You imagine two surface. One is rough, one is smooth. So still it support point number 1. If you have rough, although you don't see with the naked eyes, but there's a sharp corners here. There's a sharp corner. This is called stress eraser. In aerospace, we call it is a stress eraser that create micro crack. Okay. So that's why you see in the aerospace design in aircraft, we try to avoid rough surface. We try to polish it as smooth as we can. Especially nowadays, the aircraft we use a lot of composite. So there's a reason why we don't like rough surface. Besides, it support aerodynamics properties. On material, we don't want to have the stress eraser on the surface. Okay. And also when your car's window, especially your car's the front glass, when you have a small chip, you drive on the highway and then suddenly there's a small stone hit your windscreen. You better go and fix it. Go and fix it. Try to withhold the stress concentrator, the stress eraser on the mirror. If not, on a microscopic level, it will start to create crack, and then it will, you have one straight line there as the times go. So don't say, oh, this is more small chip only right? So you learn material already, fatigue, and then you know that you park your car in a very hot country like Malaysia. Suddenly it rains, so hot day it will expand, then it rain it will contract, expand, contract, expand, contract. Actually, you are actually helping the raise of the stress concentrator there. Okay. Okay. So these 2 points, is will help you to answer the design question, right? How to increase the fatigue strength of the design. Okay. First is you reduce the presence of stress raiser, or you focus on the stress concentration. Second one, you have a smoother surface to to increase also the fatigue strength. Point number 3 also, it actually repeated what is point number 1. It focus on the surface condition. Let's see. Point 2 is roughness, the surface condition. Oh, okay. Point number 3 here is more on the treatment, more on the surface treatment. Point number 2 is on the surface roughness. Point number 3 is more on the treatment, right? How you make the metal become stronger. So for example, those that you're familiar with, maybe not from here. For example, you do coating on your car, right? You polish, you do potting. So this one also. So for the point number 3 here, you will have, let's say you have a gear. Okay, you have a gear. Okay, you have a gear. This one you repeat. So this gear, they will do they will do treatment. They will heaten this all this gear to make it stronger. Okay. So these are all the rotating mechanism that all these gear here, they are heated up to strengthen the material. Yeah. So there are 3 points. First, stress concentration. Second, surface. The third one is the surface of the object under treatment. Is there any treatment for that one or not? Okay. Surface hardening treatments. Okay, point number 3. This one is another graph. Stress amplitude and number of cycle of fatigue. This is normal. This is a short pin. This one, short pin, PEEN, pin, is how they do it in the industry, is that they have a residual compressive stress introduced into the metal. So they use by plastic deformation within the outer surface. Okay, so there's a process there. Okay, so this one, if you want to know how they do it in the industry, you just Google, go to YouTube, then you type in short pin process, right? I think I have, okay, I have one video here. You see again, they try to polish up the surface. On the top is threatened. On the top is unthreatened. Again, the logic behind is to reduce the stress ratio. Is to make the surface smooth. Number 4 is environment. The environment of the fatigue. So if you're near to corrosion environment, for example, if you're near the sea, or you're near to the those chemical plant, then you will accelerate the crack rate. It's more on the chemical attack. On the chemical attack. The one that you see here is a damage happened on the fighter jets. Because in the operation, normally they fly into those open seas, especially those Korea, the big mothership. The seawater, the vapor will have some damage to the hinge here. There's a hinge over here. So there's this hinge will more easily to crack lah. Okay. So the crack will happen. There's a hinge on the wing here, right? This small thing where they can hook the missile or something, right? So the crack happen at all these corners. And if you observe carefully, most of the engineering design, we like to use a round shape. Because round surface, mathematically, it can help to distribute the stress. Okay, this is industrial test on how people test on the fatigue toughness test. We hope you can buy one in future, right? And there's a code. There's a code for every test. So you prepare the grip and then you mount the sample and then you start fatigue test. Again, we are now talking about fatigue, not tensile. It's continuous with a cycle. This happened very fast, although you don't see anything here. It happened very fast. And you see the graph is number of cycle versus the crack length. Crack length measured by the extentometer. This is a pre-crack. They do a small crack there and then start to do the fatigue test. This one already speed up already. So these are the data I'll get from the computer. So this is also another career that you can consider for your future. Also can make a lot of money because we need we are consumer. We almost use all sorts of material in our daily life. So in fatigue, especially in medical field, then it's you have more say in your salary. Okay. It's not very common or not very common in Malaysia, right? So far, I don't have any contacts that really expert in crack. I have expert in vibration, but not in this one. Okay. This is another graph. Correlationship between fatigue crack propagation with stress length. Crack length, they measure from here to here. When they crack, then they measure the crack length. Okay, the rest you read lah. As you read, there's a calculation there lah. Okay, this is the calculation for relating. A is the length of the crack, N is a cycle. So A is a constant, K is a constant, K is the constant, M is the constant. Right. So delta K is the stress intensity range. So we take K max minus Km. Don't worry, you don't have this one in your test. It's only for your lab practice or knowledge. Okay, because this one is there's nothing much we can ask you actually. It's quite direct. You pull and then you read from the graph. The rest you read. The rest you read. There's a calculation to calculate what is the stress intensity factor for maximum, minimum, and then how to calculate the delta K. Okay. And recall that we have lots of mode of failure. We are now talking about mode 1. Mode 1. So for the K here, is not defined for compressive stress. So if your minimum is compression, your K minimum, you put 0. Okay. The rest you read lah. So here, when you have power something, especially M, we would like to change this relationship that you see on the screen here, put in a log form. So you log left-hand side, log right-hand side. You can convert it into linear graph. Y equal to mx plus c. On the left, you can plot y. On the x-axis, you can plot log delta k. Okay, y equal to mx plus c. So this is the industrial plot or the industrial graph. It looks a bit complex, but again, on the left-hand side is your y, like the equation just now. Your y is dA dN, but in the log form. So on the y-axis is the crack growth rate, is the dA over dN. Your x-axis is your delta K, stress intensity factor range, delta K. All right, so all these you just have an observation. Okay. Okay. So on the graph here, you can find region 1 where the crack growth is very slow. Region 1, where's region 1? Here. Here, the crack growth is very slow here. It's like almost like a straight line. Okay, it's even you load it with the K factor here, the crack growth rate is very slow. Then region 2, you have a straight line. You have y equal to ms plus c. Okay, you use Excel, and then you create a straight line. It will give you a straight line. Then the third one is a rapid unstable crack. The rapid unstable crack means on the surface you see like a grass tree roots like that. Okay. So the rest is just a derivation of equation. This one you read lah from the graph. There is you from this equation, then you substitute what is K previously, right? And then you derive. Okay, this one you read lah. Not going deep into mathematics. So at the end, you arrive at one equation. Okay, you arrive at one equation, NF, which is the failure of your N, number of cycle, equal to all these parameter. Okay. So we will look at one example, or you want to have a short break? Then we go to this. After this, so very fast, example 3. You see there's a steel plate subject to a constant amplitude uniaxial fatigue cycle. So this is a fatigue for a process. Tensile and compressive stress magnitude of 120 and 30 megapascal respectively. So you have tensile and compressive. So you have a maximum and minimum. Okay, tensile, you put maximum. Compressive stress, you put minimum. The static properties of plate, you have a yield strength 1400 and a fracture toughness K mode 1 critical is given 45 megapascal. If the plate contain a uniform thickness H crack of 0.1 mm, again, what is H crack? Is your A at the side. Is your A, the A crack on the side here. This is your A. This is the H crack. The previous example you see is internal crack. Right. So read carefully the question. How many fatigue cycle can they estimate to cause fracture? So it will give you the equation. By this equation, assume y equal to 1, 1. So you pull out the equation. dA over dN equal to 2 10 power negative 12 delta K cube megapascal square root meter cube. The one on the bracket is a unit. It's a unit. So you recall what is the fatigue equation, dA over dN, A delta Kn. So your A is a constant value, 2 10 power negative 12. Your M from you compare side by side. The green color is a standard or general equation. You compare to the value given in the question. So M equal 3, Y equal 1, because the question will give you Y assume 1. Again, in your test, if your Y is not given, you assume 1. So your range of your stress, right, in the beginning of the slides, you know that range is maximum minus minimum. Okay, so in this case, your delta K, you K max minus K min. So in this case, you have a compression. So your K min is 0. So you have your 120 minus 0. We are more interested in the tensile region. Right. So again, I highlight compression from compression stress or compressive stress. In the fatigue, we ignore. Again, why we ignore? You try to imagine what is K1 mode. K1 mode is like a crocodile mouth. All right. So crocodile mouth is the one that contribute to the crack. But what happens if you do compression? You actually do not contribute to the crack. There's no crack growth in compression. You just press it. Okay. So that's why for calculation, we ignore compressive stress. So initial crack was given 1 mm. So there is a calculation. This one you learned in the previous session. So K1C equal to Y stress failure square root pi A. You put inside the equation, you rearrange, you find the crack size. Okay, you put in K1C is 45. The range you find from just now, right? Again, what is the careless mistakes in assessment is that you will calculate the compressive stress in your range. Where here, you will take 120 minus 30. Just be careful on this one. Okay, then you press calculator, you get the size of the crack, 0.449, 0.0449 meter. Then once you use this calculation, right? That there's a long derivation that you arrive at this one. You substitute all the value there. Okay, you get the failure cycle will be 2.7 something, 2.8, 10 power 6 cycle. Million, this one is a million cycle. So it will take a lot of time. Okay, so if this equation come out, I would let you know beforehand. You memorize this one. If test come out, I will let you know. You just memorize. Okay. If I tell you that, okay, you need to calculate number of failure, then you need to memorize this one. This equation won't be given in test if this kind of fatigue question come out. Okay. Okay, we stop here. We have a short break now. Okay, 10 minutes break, so we continue 9:15.